So, so once you have understood what dissolving is, now we can talk about the solubility of salts, right? So basically, you didn't understand, Zores? You didn't understand? Basically, see what happens in dissolving. Did you just join, or were you there already and you heard me and you still didn't understand? Or you just joined? Zores, did you just join, or were you there and you still didn't understand? Wajiha, you understood, right? And Hassan, you did. You just joined. Yeah, that's why. Okay. See, beta, if you guys come late, I cannot recap for those who are coming late, because then the ones who have already joined, they are at a disadvantage, right? I have to move on. Okay, and I just remembered to record. I just started recording. Okay, I'll see. Okay, I'll see. Stay with me. You will understand, and I might recap. Okay. Now, when an ionic compound dissolves, the polar water molecules attract the ions away from their regular arrangement and surround them, so the ions get into the spaces between water molecules. So did you notice that salt crystal, the cations and the anions of the salt crystal were getting adjusted in between the water molecule? You can even look at this diagram. Can you see these are the water molecules? In between these two water molecules, by the way, this is also water molecule. Okay, so in between these water molecules are these cations and anions, right? This is an anion and this is a cation. Now remember, anion is usually bigger than a cation. Why? Why is an anion bigger than a cation? Why do they always show anion as a bigger circle and a cation as a smaller circle? Any ideas? Do you know why anion is bigger than a cation? Any guesses? No? Okay. Yes. Okay. Because you see, anions have gained an electron. Yeah, anions have gained an electron, and there is repulsion between the negatively charged electrons, right? So that will lead to an overall increase in the size of the, the whole particle, the whole anion, whereas cations have lost an electron. The cations have lost an electron, and so the leftover electrons get a little closer to the nucleus, or they get a little closer to the protons of the nucleus, and therefore the overall size of the cation is smaller as compared to the anion. Anions have gained one more electron, and so the negativity increases, and so the electrons repel sort of from each other, and so they go farther away, and so increasing the size, the overall size of the anion. That is why anion is always bigger than the cation. Okay. Okay, so basically when a salt is dissolving in water, it is trying to get in the space between the water molecules. The cation and the anions of the salt are trying to get into the space between the water molecules, right? So this is what happens in dissolving. So this is a salt. Okay, I'm recapping. Okay, Zores and Hassan Wali. This is a salt before dissolving. This is the salt before dissolving. Okay, can you see the salt is in its regular solid arrangement? I have used two different shapes. The dots are the cations and the bigger circles are anions, and these are water molecules, right? And so this is before dissolving, right? This is a solid ionic compound. It hasn't dissolved as yet. I just added the salt. Now, after I've stirred, I have dissolved it. This is what happens. The anions and the cations have dispersed, they have scattered, and they have accommodated themselves in the space between the water molecules. So dissolving is basically the ions, the positively charged and negatively charged particles, have gotten into spaces between the water molecules. This is what happens when an ionic salt dissolves in water, right? So this is the thing that I just explained, right? So they have gotten into the spaces between the water molecules. Okay, let me show that video again. Yeah, let me show that video again. It was a short one, so it's okay. I can. Now, this will show you how a salt dissolves in water, right? It will first show you the water molecule. The green small caps are the hydrogen atoms, and the bigger blue ball is the oxygen, right? Now, there are lots and lots of water molecules surrounding this solid salt. You can see the bigger pink circles are anions, the smaller yellow circles are cations. Now, they have shaded the positive part of the molecule red and the negative part of the molecule blue of the water, right? Here, the bigger circle is the anion, the smaller circle is the cation, right, of the salt. Right, now the salt will dissolve in this water. The positively charged part of the molecule, of the water molecule, is surrounding the negatively charged ions because of the opposite charges. Now, the positive part of the water molecule, the negative part of the water molecule will surround the positively charged cation of the salt. And that's how the water molecules will surround each cation and anion. So you can see that the ions are trying to accommodate within the spaces between the water molecules. Each cation and each anion, one by one, is getting pulled out by the water molecules. And now can you see that the ions are trying to accommodate in the space between the water molecules, right? So this was the video that I showed, and this is showing how the ions or the salt dissolves. Yeah, you are not supposed to hear the video. You cannot hear the video in Zoom. So that's why I'm explaining. And there's nothing in the video. The video is without anything. Okay, so, okay. So now my question is, can we just go on adding the salt to a particular amount of water, you know, unlimited, or is there a limit to the amount of salt that we can add? Huh? My question is, for example, this is my beaker and these are the water molecules. Now, if I add salt into it, then the salt will try to accommodate in between, in the spaces. It will try to accommodate the space in between the water molecules, right? Now I'm adding. I will keep adding, and then there will be a time when there is no space left. There is no space left. Yeah, if now there's no space left. Now, if I keep adding, now what will happen? If I keep adding, now these molecules cannot shrink, you know, like I'm drawing smaller circles, but they cannot shrink. They need space. They need a space. Now, where to go, right? Now, this is, then what they do is that they start arranging themselves back into the solid form. They start, now these salt ions, these cations and anions of the salt, which I have represented, by the way, same color, okay, green color, are my cations and anions of the salt. Now they will start arranging themselves in the solid form back again after all the intermolecular space has been occupied. When there is no more space left in between the water molecules, they start arranging themselves in the solid regular form, and that's when we get the solid crystals back again. Remember in evaporation, Zores, this class was for 6th graders. Okay, Zores, this class is for 6th graders. Okay, so yeah, I know you don't know about ions, so just absorb. okay, whatever I'm saying, and then inshallah, when it will be your time, you will understand it better. Okay, so now these remember when we were evaporating and when we were heating with the help of water bath, and we stopped heating when we started seeing the crystals. Remember, we stop heating when we start seeing crystals. So what are we doing in evaporation? In evaporation, the water molecules are leaving, right? The water molecules are leaving because we are heating them, and so water molecules leave. And as the water molecules leave, there are less intermolecular space. There is no space in between the water molecules, and so these ions of the salt do not have a space to accommodate themselves, and that is why they start arranging themselves in the solid form, and that's when we start seeing the crystals. Now, I got another video where that video will show you how by continuous addition of salt to water will lead to crystallization. Crystallization meaning that the salt cations and anions will start rearranging themselves back into their solid form after dissolving. First, they had dissolved. So first, the video will show you how the ions, how the salt is being added. Initially, they will show you the ions dissolving, and then they will continue adding more and more ions. And so gradually you will see that those, after all the space has been, I mean, in the video, they have not shown that all the space has been occupied, but the video is showing how the ions, after a point, will start rearranging themselves back in the solid state, okay? So I thought it was helpful. So therefore I got it for you guys. Yes, Hassan Nadeem, that's right. The ions will start piling up. Yes, okay. Let me. Oh, what happened here? Wait. Now he's adding salt. He's adding salt. Now you can see that the cations and anions are dissolving in the water. The cations and the anions are dissolving in the water. Now we have lots and lots of them within the water. And can you see at the bottom that the ions have started arranging themselves back in the solid state? The ions have started arranging themselves back into the solid state. Now he is now showing you another animation. Again, you can see that the ions are piling themselves back into the solid state. Can you see that at the bottom? How they are rearranging themselves back into the solid state. Okay, so this is what happens at the point of crystallization. This is called point of crystallization. How do I get back? Yes. Okay. Okay, so did you guys understand this crystallization? Did you see how did you guys understand this crystallization? Your screen is stuck. No, my screen was fine. You couldn't see the video? Oh, you couldn't see the video. Okay, okay, okay. No problem. I'll show you again. Wait. Okay, I'm sharing again. This video is showing you crystallization, how by a continuous addition of ions of salts, after the solution has achieved its limit, And if you continue adding ions, see, now he's adding salt into the water. Now the cations and anions are dissolving in the water. Okay, the cations and the anions are dissolving in the water. He keeps adding, and now you can see there are lots and lots of ions, so much so that at the bottom you can appreciate the cations and anions are piling up again into their previous solid arrangement. Now he's showing another salt. Again, there are lots and lots of ions in the solution. Okay, and you can see that the ions, the cations and the anions have started piling up on each other at the bottom. So they are like crystallizing again. They're again resuming their solid arrangement. Right? This is called crystallization. At this point, the solution is said to have reached its point of crystallization. What? You did not see? What's happening? We could only hear your voice, neither can I see. I couldn't see the video. Again you could not see, even the second time. I showed you twice. Please let me know. Okay, Hassan Nadeem, you saw. Okay, Hassan, you saw. Okay, good. Good. Okay, so did you understand what I was trying to explain? Yeah, okay. Did you see that how the cations and the anions were crystallizing back again into their solid arrangement? Okay, good job. Yes, that's what I was trying to show you. Yes, okay. So did you see now, at this point, the solution is said to have reached its point of crystallization, right? This is called point of crystallization. Now, what is a crystal? Crystal is nothing, it's just a grain of solid salt. Crystal is a grain of solid salt, okay? We use the word crystal for the solid grain of a salt. Whenever you come across this term, this means solid state, right? So there's a limit to the spaces between water molecules. When we keep adding ions meaning salt, to the water, a time comes when there is no space left between molecules. At this point, if we keep adding ions or salt, these ions will start piling up again, with cations attracting anions and therefore rearranging themselves back into their solid form. This is called a crystal. This is the point of crystallization, meaning at that point where you see the first crystal, even a shiny glimpse of a little tiny crystal, that point is called the point of crystallization of that solution. Now, of course, crystallization or the point of crystallization will be achieved only and only when all the intermolecular space has been occupied, meaning that there is no more space even for a single ion of the salt in between the water molecules, okay? Like, something like this. Now, not a single molecule can come and sit here, and therefore, at that point, the solution is said to be saturated. The solution is said to be saturated. Now, the word saturated means like limit. That's it. No more. Not a single ion. Okay. They are showing this cartoon here in this I don't know what the page number is. The same page. These are the ions. And the cartoon says, pool closed, saturated solution, no more dissolving, like no more ions can come in. Sorry. Okay, no more ions can be accepted because there is no space. Okay, so solution at this point is called a saturated solution. Yeah, Zores, these guys have new book. Their numbering of pages different from mine. So it's 131 with me, but it might be different with them. Okay, so what is, okay, 204, okay. Saturated solution means a solution that cannot take or dissolve any more solute. What is a solute and what is a solvent? You guys know that, right? You guys know that. What is a solute and what is a solvent? A fresh piece of page. What is a solute and what is a solvent? No? You guys don't know? What is a solute and what is a solvent? No? Yes. Yeah, solvent is not necessarily liquid. It is usually liquid. Yes. Like for example, you had something and then you added something into it. Okay. So yeah, usually in normal cases, this is the liquid, but I will call this solvent into which I am adding something. And that something that I'm adding is called a solute. Right. Now this can be any state. It can be solid, it can be liquid, it can be a gas. And same is the case with solute. It can be solid, it can be liquid, it can be gas. But usually for your level, for grade 6, we usually take solvent to be liquid and solute to be solid, okay, to make things easier. So solvent is liquid and solute is solid. But when you are asked to define solvent and solute, you should not use the word solid, liquid, or gas because it can be any, right? Solvent is a part of a mixture into which something is added. Okay, mixture is when any two substances are mixed. Mixture is when any two substances are mixed. Now we have different types of mixtures. Okay, solution is one type of mixture. Then we have other types of mixtures such as suspension, and then there are types of suspensions as well, and so on and so forth. So no need to go into details, but you should know the basic idea: solute, solvent, and mixture. Now, what happens when we evaporate? Now, as we evaporate a solution, we are further decreasing the intermolecular space. Why? Because the solvent molecules are leaving the liquid. The water molecules are leaving the liquid. And so we have less and less of water molecules left behind. And so, you know, it's just like decreasing the number of rooms. If you decrease the number of rooms, less people can be accommodated. Right now, more salt can be added into this water than this, right? More salt can be added into this water than this because there are more water molecules, more intermolecular space, basically more rooms. Here you have less water and therefore less intermolecular space, therefore less salt can be accommodated in here, right? So what evaporation does is that it decreases the amount of solvent and therefore we have less intermolecular space and therefore less salt can be accommodated or can be dissolved, right? So evaporation enhances crystallization. Why? Because there is less space, so the salt, this will reach its saturation point earlier. This will reach its saturation point earlier, and the salt will start arranging themselves back into the solid form quicker or earlier. So you will see crystallization taking place earlier in case of an evaporated water, or, you know, as a result of evaporation. That's why we keep evaporating till we see crystals, till we see crystals. So at the point where you see the first crystal, you know that this solution is saturated. That's why you start seeing crystals. That means no intermolecular space left. Okay, and so you stop heating because you don't want to overheat, because you don't want to damage the crystals. And then you let the room temperature do its job of continuing the evaporation, and then that you will end up with bigger, nicer, shinier crystals, right? Okay. So as we evaporate a solution, we are further decreasing the intermolecular space, therefore more ions deposit in their regular solid form arrangement, therefore bigger crystals, right? Okay, now I hope you understood the dissolving and the solubility concept. Till here, does anybody have any question? Ask me. What happens if you damage the crystals? Nothing happens. Your crystal is damaged. That's all. You won't have nice crystals. That's it. If you want nice crystals, you will have to follow these instructions, these whatever, you know, you have to be careful with your warming. You have to stop heating. And even if you are heating with the Bunsen burner, you have to be real gentle. And that's why we use a water bath. Remember, we do not evaporate directly above a flame or above a heating source. Okay, we use a water bath or even a sand bath. Even a sand bath is acceptable. Any questions so far, or should I move on? Should I move on? Okay. Can you then salt into liquid? You mean to say that can we convert salt into liquid? Yes, by melting. Yes, you can. After you have achieved your crystals, after you have, you know, gotten your crystals, then yes, you can melt them. But then you will have the liquid form, not the crystalline form. Is my screen hung? Is my screen hung? No, it's not. You guys check your connections. Okay, good. Okay, now let's check your connections, because I checked my connection, it's fine. Okay, solubility curves. Now we were to talk about the solubility curve. Now solubility curve, okay, first I will talk about what is solubility. How do you measure the solubility of a salt? Now we can define the solubility of a salt as the mass of salt that dissolves in a specific amount of water. Now, what is that specific amount of water? All the scientists agreed so that, okay, let's take 100 grams of water to be the standard, right? 100 grams of water. So they chose 100 grams of water. Okay, so now solubility's definition is the mass of salt that can dissolve in 100 grams of water. Simple. Okay, solubility of a salt is defined as the mass of salt that can dissolve in 100 grams of water. Now we know that the density of water is 1 gram per cm cube, right? Agreed? This density helps us a lot because it's easier to convert the mass into volume. By the way, it is the same for ml as well. Why? Because 1 cm cube is equal to 1 ml. So we can also say that 100 grams of water is equal to 100 ml of water. Okay, so 100 gram has a volume of 100 cm cube of water, or 100 grams has a volume of 100 ml of water. So the amount of salt, mass of salt in grams that dissolves in 100 grams of water is the solubility of that salt. Okay, now once you understand that, now let's move on to the solubility curves. Okay, again, this is the same picture on page 204. 204, you can look at your books if you have. Otherwise, I am sharing my screen. I am sharing my screen. This, yeah, solubility curve. Now they have chosen 3 salts: potassium nitrate, potassium chloride, and sodium chloride. And now what are these 3 curves showing us? That as we are increasing the temperature, the solubility of salt is increasing, right? Now, why? What is the effect of temperature on solubility? Now, again, going back to what happens when salt dissolves, let's understand. What happens when salt dissolves? They try to get into the spaces between the molecules, right? They try to get in, when the ions dissolve, they're trying to get into the spaces between the molecules. What does the temperature do to the water molecules? It increases their kinetic energy. It's okay, Hassan, you can just refer to page 204. Okay, I was showing the same picture. Okay, 204, solubility curve. So we are discussing the effect of temperature on solubility. Yes, Wajiha, you are correct. As we increase the temperature, we are increasing the kinetic energy of the water molecules. And so water molecules are bumping with more energy, and they are colliding with each other, and they are moving faster. And what else? They are moving farther away from each other, right? And so the space between them is increasing, right? So you can say that the rooms are getting bigger and bigger. The room is like space between the molecules, right? No, we are not turning liquid to gas. We're just warming the water a little, okay? We are not warming to the boiling point. We are not heating the liquid till the boiling point. That's when you have liquid turning into a gas, right? We are not going all that way. Just a little warming. So we are increasing the kinetic energy, right? And so they are moving farther away from each other. So like we are increasing the size of the rooms, and therefore more ions can accommodate. Of course, more people can fit into a bigger room, right? So therefore more ions or more salt can fit into bigger rooms, which are the intermolecular spaces, okay, space between the molecules. So as temperature increases, the space between molecules increases, and therefore more ions can be accommodated in between the water molecules, and therefore more salt can dissolve in water. And so we say that the solubility of salt increases, okay? And this is the reason that whenever we talk about solubility of salt, we do not forget to mention the temperature. Like, you know, if we say that, for example, the solubility of copper sulfate is 19 grams per 100 grams of water, but at what temperature are you talking about? Are you talking about 10 degrees Celsius, 20 degrees Celsius, 15 degrees Celsius, 40 degrees Celsius? Because the amount of salt that will be dissolving in that 100 grams of water is going to vary depending upon the temperature. So what temperature are you talking about? So you got to mention the temperature whenever you are talking about the solubility of a salt, okay? So 19 grams per 100 grams of water at 15 degrees Celsius, okay? Standard temperature is 25, right? Or is it 20? 25, yes. The standard temperature is 25. If the temperature for any reason is not mentioned, then we will assume that they are talking about the standard temperature and pressure, which is 25 degrees Celsius, okay? So that was that. Now, let's answer these questions. Which of the three salts is most soluble at 20 degrees Celsius? I am reading the questions on page 204 of your book. Regarding this graph, which of the three salts is most soluble at 20 degrees Celsius? Yes. Which salt is the most soluble at 20 degrees Celsius? So let's look at this graph. What's happening at 20 degrees Celsius? See, with the help of a pencil, I drew this line so that I know exactly what's happening at this particular point, 20 degrees Celsius. Which line is at the top? Now they have drawn the three graphs with three different colors, which is helpful. Okay, so now at this point, 20 degrees Celsius, which salt has the most mass dissolved? That salt will be the most soluble because it has the most mass dissolving in 100 grams of water. So which salt is it? Which line is at the top? Yes, good job. It is sodium chloride. Yes, Wajiha, it is sodium chloride. Riaz, why did you say potassium nitrate? Blue line is at the bottom. Blue line is at the bottom. Can you see the blue line is at the bottom? So it has the least mass dissolving in 100 grams of water. right? And then this red line, which is potassium chloride, is in the middle. So if I arrange them in order of decreasing solubility, okay, it would be green, red, and then blue. Green is sodium chloride, red is potassium chloride, and blue is potassium nitrate. Okay? Is it clear? Yeah, it's okay, but did you understand, Riaz? No need to be sorry, but did you understand? What, Hassan? What's the potassium nitrate? What? Potassium nitrate? No, potassium nitrate is not the most soluble. It is the least soluble. You don't understand? Okay, look at this picture. I'm sharing my screen. Now, if you want to know which salt is the most soluble at 20 degrees Celsius from this graph, what will you do? You will mark this point 20 degrees Celsius, and I would recommend that you draw a straight line parallel to the y-axis, passing through 20 degrees Celsius on the x-axis, and then observe which line is at the top, because the line at the top will represent the salt, the most mass of which is dissolving in water, which has most of its mass dissolving in water. Okay, if you cannot understand, then I will use my video. Okay, I will use my video. Okay, so here, this is the mass that is dissolving for sodium chloride. Mass for potassium nitrate, sorry, potassium chloride is this. Can you see it is below? It is below sodium chloride. This is sodium chloride. This is potassium chloride. And then this would be potassium nitrate. So it is the least. So potassium nitrate mass dissolving at 20 degrees Celsius is the least. Can you see I am extending the line where this blue line is touching the 20 degrees Celsius mark here? Did I make sense? Did you understand, Hassan? Did you understand? Okay. Did you really understand? Okay. Now let's move on to the next question. Which salt is most soluble at 60 degrees Celsius? Yes, that's potassium nitrate. And then again, followed by potassium chloride, and then sodium chloride. Here at 60 degrees Celsius, it is potassium nitrate. And can you see that the solubility difference is so big? It's so big. Here, the difference was not as big, but here the difference is too big. Now, another thing that you will observe in solubility curves is that, you know, when the temperature is too high, at higher temperatures, the graph goes up really steeply. You know, the graph goes up really steeply like this. So that means here at lower temperatures, the solubility is increasing, but it is increasing very gradually. And as the temperature is too high, the solubility increases dramatically, drastically. Why? Because now they're going so far, they're near their, maybe, you know, they're near the boiling point, or they're going farther away from each other. The rooms have increased too much. And a time will come when the liquid will reach its boiling point and it will turn into a gas. Okay, but we have not reached there. But yes, at higher temperatures, the solubility increases drastically and dramatically. Okay, so you will see that the curve becomes vertical, almost vertical. Right. Okay, then let's talk about this investigation. 10.6. Which salt is most soluble? Okay. You can test the solubility of these salts. Okay. Design a fair test to see which of these salts is most soluble. Use 10 cm cube of water for each test. What other variables must be kept constant for a fair test? So Can you guys come up with any ideas regarding a fair test to see which of these salts is most soluble? Any ideas? It's okay. We are all here to learn. Design a test, design an experiment. If, for example, you are given these 4 salts, copper sulfate, sodium chloride, calcium chloride, and zinc sulfate. Now, somebody asks you, tell me, which of these is the most soluble? How would you figure out? How would you find out? Or with your given knowledge, with whatever knowledge you have, what experiment can you come up with? Any ideas? Yeah, all the 4 salts, all the 4 salts. I hope you have your book with you. I'm talking about this experiment. Which salt is most soluble? Design a fair test to see which of these salts is most soluble. Use 10 cm cube of water for each test. It's okay, you can make mistakes. It's okay, we're just suggesting, we're just discussing. You won't be marked on this or anything. Yes, good job. All must have the same temperatures. Why should they have the same temperature? Galaxy Note 9, can I know your name, your real name? Yes, you are right, but okay, Smile, tell me, why should the temperature be the same? If you think typing is too difficult for you, you want to give answer orally, then you can raise your hand and I'll unmute you. Yes, good thinking, Zores. We can use 100 ml, not 100 ml. They have told you to use 10 cm cube of water. Yeah, because when we are comparing, we are only comparing the solubility, okay? The rest of all the factors should be kept constant, especially those factors which might affect the solubility, right? So, okay, I have come up with an idea. I will take, they're raising their hands. Let me see. No, I cannot see any hands raised. Okay. See, I'll tell you. Okay, now listen to my idea. This was my idea. Okay, I came up with this. I will take all of these salts. I will take their, I will take all these salts, and then I will take 4 beakers of water, right? I will take 4 beakers of water exactly. Yes, and each of them will contain 10 cm cube of water. Each of them will contain 10 cm cube of water, and I will also use thermometer for each and every beaker to make sure that the temperature is the same in all the 4 beakers, right? Let me draw what I am saying. Let me, so that it's easier for you to understand. Okay, so these are my 4 beakers. Can you hold this? These are my 4 beakers, and I will take the same amount of water in all 4. Why is it important to have the same amount of water? Why is it important to have the same amount of water? Any ideas? Come on, come on. Beta, yes, you are right, so that the results don't vary, but how would they vary? If my volume of water is not the same, how would it vary? See, remember I told you that if the water is less, there will be less intermolecular space. Yes, so there will be less intermolecular space, and so less salt will dissolve. Yes. No, not that some would dissolve and some would not, but because see, if for example, remember I drew this, zoom out. For example, I have two different amounts of water. So of course, more salt will dissolve in this compared to this, right? So I cannot say that now, of course, this will achieve the point of crystallization sooner, and this will achieve point of crystallization later. This will get saturated later. This will get saturated sooner because it had less water molecules, right? So I cannot say that, okay, the solubility of this salt is less because, you know, it got saturated when I added only 10 grams, and this did not achieve saturation even after I added 40 grams, but that was because the amount of water was different, not because the salt was less soluble or more soluble, right? So when you are designing an experiment, remember that your results, nobody should be able to argue with you, oh yeah, you got this result because of this or because of that. So keep all the conditions identical, especially those conditions which might affect the results of your experiment. So the amount of water can affect our experiment. The amount of water can affect, you know, our results. So it is very essential that all the containers, all my beakers should have exactly 10 cm cube of water. Also, the source of water should be the same. Source of water should be the same, because I don't want any water to be dilute, the other to be concentrated. Because remember, tap water also has some ions already present in it. So the room is already occupied. The rooms are already occupied by the ions. Remember? Yeah, we can use distilled water. Now, if you use distilled water, well and good, then that's perfect. So make sure that you are using distilled water for all the 4 beakers. But if you are using tap water, make sure that the source is the same, from the same tank, from the same tap, right? So whatever it should be, whatever factor might be changing, it should change equally for all 4 of them, right? And then my beaker should also be of the same material. The beaker should also be of the same identical material. Why is that important? Well, some material might be, yeah, more conducting than the other, or some material might be a better insulator than the other. Now, insulation and conduction will affect how they are getting, how they are absorbing the heat from their surroundings. And so if a beaker has more conduction than the other, it will be absorbing more heat, and therefore it would be warming the water up and therefore increasing the solubility. And so that will affect our results. So the material with which the beakers are made, the amount of water, the volume of water, and also the source of water should be identical. Okay. Now, once we have, and also we should have thermometers to know that the temperature is constant. Okay. The thermometer will also help us. Okay. If, for example, any temperature is less than the other, we can warm it a little, and so bring the temperature equal to the rest, so that all the temperatures are the same, right? And then we will start adding salt. Okay. Now we will start adding salt in a specific sequence. Like, for example, you can choose, and you should already know what the solubility is. So like, you can start by adding 5 grams at a time, or maybe 1 gram or 2 grams, but whatever value you choose, you keep it constant. Okay. And you will weigh the salt first, make sure it is 1 gram, make sure it is 2 grams, and then you add. Okay. And then you add. So you have to weigh the salt before adding, because once you have added, you cannot weigh then, right? So weigh it, and then you add, and then you keep adding, and you keep stirring with the help of a glass rod. Why is stirring important? Stirring is important in order to fasten the dissolving, to help in the dissolving of the ions, because remember, stirring helps in dissolving. So you keep stirring with the help of glass rod, and remember, stirring affects dissolving. So all the 4 beakers should be stirred to the same extent. Yes, that is difficult and it's time consuming. So you will make sure that all the 4 beakers have the same amount of stirring, okay? And then you will keep a very vigilant eye on the crystals. You will keep adding till you start seeing crystals, even one crystal here, even one crystal here, and then you will stop adding. That will be your saturated, that will be your point of crystallization. That will be your saturation point, the saturation point of this solution. So you will stop adding and you will note down your value. For example, you saw this crystal at 40 grams. Okay, and let me write down the names of the salt. For example, this is copper sulfate, this is sodium chloride, this is calcium chloride, and this is zinc sulfate. Okay, so yeah, if you, as soon as you see the crystal, you will stop adding and you will note down the value. Okay, for example, 40 grams is the value for zinc sulfate. For example, 50 grams, I'm just taking random numbers. 50 grams was the value for calcium chloride, or let's suppose 60 gram was the value for sodium chloride, or 20 grams was the value for copper sulfate, and so on and so forth, right? And then you will, and this is how we plot solubility curve. And then we can change the temperature, okay? And then we can change the temperature, and let's suppose, you know, we warm them all a little and bring them to a new temperature and repeat this whole process. And that's how they plot this solubility curve for different salts, right? Okay, somebody asked questions. Let me see. What if by mistaken mix one more than the other? What will happen then? Yes, then your results are not reliable. Then your experiment is flawed. Okay, then you will have to repeat your experiment. Yes, it needs a lot of practice. And then there is a margin of human error. Like you can be 5 grams up or down. You can be 5 grams more or less, but not more than that, right? Of course, we are all humans. Humans make mistakes, right? We cannot be 100% perfect. There are a lot of places where we can make mistakes. Okay, there can be unequal stirring. There can be mistake in recording the temperature. There can be mistake in measuring the water. There can be a lot of problems, right? So we will go with approximate values. Okay, we will make sure that the flaw is not too much. Okay, now let's try to answer these questions. What other variables must be kept constant for a fair test? So they told us to keep the volume of water constant, 10 cm3, but what other variables must be kept constant? And you guys told me the temperature, which is very good. Other variables that I suggested was that the source of water, same thing, Ismail, a water level or the volume of water. Of course, when the volume is the same, the level is also going to be the same, right? And then the mass of salt, of course, is the variable that will vary, okay? And then another thing is that also make sure that the 4 types of salts, all of them are equally fine powder, equally finely powdered. Okay, yeah, they might be toxic Zores. You have to be careful. Okay, you have to be careful with, you will follow all the safety precautions. Okay, you will follow all the safety precautions, wear your gloves, your goggles and everything, right? So if, for example, one salt is having bigger crystals than the other, and the other has smaller crystals, for example, you have calcium chloride in this form, and you have zinc sulfate in this form, then of course this will dissolve faster. You will have more solubility for calcium chloride. So make sure that they all are in the powdered form and their crystals are of the same size. So yeah, that is another problem you might get, you know, wrong there. Bigger crystals will take longer to dissolve. Smaller crystals will dissolve faster, right? Because more surface area available. So make sure that the grains of these salts are also identical. Yes, good job, Hassan. Yes, yes. Yeah, we can crush them. Yes, exactly, Zores. Good job. Good idea. If you think that the size of the crystals of one salt is bigger than the other, we can crush them using the mortar and pestle. We can crush them, right? Okay, so keep adding salt till crystals start appearing. This is when the solution is said to be saturated. We will measure the weight of the salt before adding, okay? Exact point of crystallization may be missed, So make use of known solubility at an intervals. Like for example, there was a little crystal there, but you missed it because it was too small. And so you, by accident, you added 1 more gram. And then when there was a bigger salt, then you saw it. So that's another possibility of a mistake. So you have to keep a vigilant eye. Okay, keep an eye for even the smaller crystals. Okay, how can you tell when your solutions are saturated? When crystals are formed, exactly when crystals are formed. Now, Wajia, yes, you are right, but what will you see? How can you tell? See, you have to, they're asking, how can you tell? How can you tell that the solution can dissolve no more? When crystals start forming, right? How will you measure how much of each salt dissolves? You will pre-weigh, you will weigh before adding, and then you will stir, okay? If no more is left behind, if you cannot see any salt and it is disappearing, that shows that it is dissolving, right? Right. Why is it difficult to collect precise and accurate data? Because of human flaws, because of human errors. And there are so many possibilities of human errors in this particular experiment of ours, right? Right. So we are out of time. I wanted to do a question. Can we do just one question? This, I know we are already out of time, but just this question. Question number 8 with me. Do you guys have it? Do you guys have this question? Look at the table. This is the end of chapter question. You don't have it in your book? Look at the table below. It shows the solubility of potassium nitrate. It is omitted? I don't think so. I think it is included. If this page is included, this question is included because this question is based on this page. Okay, even if it is omitted, it's okay. Let's do it because it is related to this page, exactly related to this page, 204 that we have just read. See, Moaz, it is 138 in my book. You have it, Hassan? Okay, good job. Let's do this question real quick. Okay, we'll be done in 10 minutes. Okay, okay. Look at the table below. It shows the solubility of potassium nitrate at different temperatures. Okay, so just like, so this is potassium nitrate. Draw a solubility curve for potassium nitrate. See page 131. 131 is the same as your 204. This solubility curve, can you see? So they're asking us to draw this graph with the help of this table. With the help of this table. So your x-axis would be the temperature and your y-axis would be the mass of salt dissolving in 100 grams of water, which is solubility. So I drew this graph. I don't know if it is clear. Let me share it. I took a picture of it. Let me share it. Here, this. Now, my y-axis is the mass of salt in grams, which is dissolving in 100 grams of water, which is the solubility of the salt, and the x-axis is temperature, right? And when I plotted these values that they have shown in the table, this is the shape of the graph I had, which is exactly the same as the shape on your page 204, right? Now, what pattern can you see from your graph? That's part B of the question. What pattern can you see from your graph? So how will you describe the pattern here? How will you describe the pattern? Yes, let's see. Can you describe the pattern of solubility of potassium nitrate looking at this graph? See, first of all, you will tell me whether the solubility is increasing or decreasing with temperature. That's the first thing, because x-axis is temperature, y-axis is the solubility. So you are studying the effect of temperature on solubility. So what do you think? Yes, Wajiha, good job. Yes, solubility is increasing with increase in temperature. Ismail, how can you say that it has been saturated? Just by looking at the graph. Just by looking at the graph, how can you conclude that the solution has been saturated? No, you cannot make that conclusion. The graph does not show where you were having saturation. Okay, so you will not say that, because see, you will mention only what you can deduce, what conclusion can you make out of the graph. So in the graph is only showing that as the temperature is increasing, more and more mass of potassium nitrate is dissolving in 100 grams of water. That's all you can make out from this graph. Is there anything else you want to talk? Remember what I told you, that at lower temperatures, the increase in solubility is gentle, is gradual, and at higher temperatures, the graph becomes more vertical, and that means the solubility is increasing sharply at higher temperatures, right? So mention that as well, that at higher temperatures, this increase in solubility of potassium nitrate is more, or is sharper, the increase is more, right? Okay, what is the solubility of potassium nitrate at 50 degrees Celsius? 50 degrees Celsius. So, okay, I have not shown it here, but I have shown it here. Okay, so I hope you can see it. This is, can you zoom in a little, but just show this part. 50, not too much. I want the whole graph to show. Okay. So at 50 degrees Celsius, this is 50 degrees. Okay, I will darken it for you. This is 50 degrees. Okay, and if I measure the corresponding value on the y-axis, I am getting 85 grams. 85 grams. And so I know that 85 grams of potassium nitrate dissolves in 100 grams of water at 50 degrees Celsius. Okay, 85 grams of potassium nitrate is dissolving in 100 grams of water at a temperature of 50 degrees Celsius. Now the second part is asking solubility of potassium nitrate at 70 degrees Celsius. So this is 70 degrees Celsius in my graph. Okay, I will go up, okay, all the way till the graph, till I meet the graph, and then I read the corresponding value on the y-axis. And so I got 135 grams. This is 135 grams. Yes, okay, yeah, 134 grams. Okay, 135 grams. Yeah, you can be 5 values up or down. It's okay. Okay, it's allowed. Okay, now what does a saturated solution mean? What does a saturated solution mean? I told you, anybody remembers? Saturated, the word saturated means? Yes, what does the term saturated mean? Yes. No. I like trains. You are close. What's your real name? If we would have 5 values up or down, it wouldn't matter at all. Yes, for examination purposes and okay. For examination purposes and even for experimental purposes, yes, they do allow for human errors. We cannot be 100% perfect, but not too much, not more than 5. If your error is more than 5, then yes, you will be penalized. Okay. Yes, Hassan Ahmad, yes. Your answer is to the point. Yes, I mean, that's the actual answer. Saturated solution means a solution that cannot dissolve any more solute. Remember, this is the definition for saturation. Yes, I know you guys got the idea, you know, that there's too much solute, but how much? How much is too much? Okay, remember, in scientific answers, you do not use vague terms. You do not leave on the reader to guess. Okay, you have to specify exactly what you mean. So you have to say, yes, when a solution cannot dissolve any more solute, that solution is called saturated. Yes, Ismail, yes, it has reached its limit. Yes, good job. Now, how can you, part E, how can you make a saturated solution of potassium nitrate? No solid should be present. So they just want to know if you know the steps involved in making a saturated solution. So how do we make a saturated solution? We discussed when we were designing this test, what were we doing? When we were designing this experiment, when we were comparing the solubilities of these four salts, that's what we were doing. We were preparing saturated solutions of each of them, for each of them. So how do we make a saturated solution? We take a known volume of the solvent, which is water, okay, and we regulate its temperature with the help of thermometer, okay, and then we weigh the mass of salt, and then we add, okay, gradually we keep adding constant amounts of salt, and we also keep stirring, okay, till the point where you see crystals. The moment you see even a tiniest crystal, you stop adding and you say that a saturated solution is ready. A saturated solution is ready, right? But the question has at the end also mentioned, no solid should be present. So that means they don't want you to have any crystals. They don't want you to have any crystals. So yes, if there are any crystals made, we can easily filter it out because it is solid and it is not dissolving at that temperature. So any insoluble solid in a liquid can be filtered out. Yes, good job, Wajiha. Okay, so with this, we come to the end of this chapter. I wanted to do more questions, but it's okay. We will do more questions on Monday, maybe. Yeah, 4 to 5, Monday, right? So any question? Any question regarding what we discussed today? Okay, no? Are we good? Yes, Zores, you want to ask something? Yes?
I wanted to ask, why does potassium nitrate, why is it more soluble at higher temperatures but less soluble at lower temperatures, and the other salts are more soluble at lower temperatures and less soluble at higher temperatures?
Yeah, okay, that's a good question. See, solubility has to do with the bonds that have to break, because remember what is happening in dissolving. I showed you the videos, right? What's happening? So basically, okay, let me draw a diagram and show you. See what's happening. Can I have a marker? So this is a salt, right? This is a salt, and then water molecules are coming and pulling them out, right? So there is bond breaking. These are breaking. These are separating, and then new buddies. It's making new buddies, right? So when making new buddies is easier than breaking, they break off and they make better friends, right? Like, I mean, for your level, just understand that if, for example, you had a friend, but that friend was not too good to you and you were not that attached to him, and then suddenly you made a new friend and that friend is way better, is a better person. So it's easier for you to break off your friendship with him and then make friends with these water molecules, right? This is the best explanation I can give you for now. But so it depends upon how strong these bonds are between the cations and the anions, okay, and how much energy is being released in the formation of these new weaker bonds. So it all has to do with this, okay? Some have really strong bonds, so they need a lot of energy to break and then dissolve. Some are very weak, so they break even at room temperature and they're highly soluble. So it depends upon how strongly these cations and anions are bonded to each other in their solid arrangement, right? That will decide how easily they are soluble. Okay, I hope you got a rough idea. But we cannot exactly explain why some salts are more soluble and some are less. But yes, it has to do with the energy required to break the bonds and the energy released when they are making newer bonds with the water molecules. So potassium nitrate has a weak bond. Yeah, you can say that. Yes, you can say that, sort of, yes. Can we do next class on Sunday? Yes, next class is on Sunday for fifth graders. I will be teaching them, you know, that formula writing and balancing equations and all of that. That will be on Sunday. So on Monday, we will do questions regarding this chapter, acids and alkalis. Okay, is there any other question? Yes, just like last week, just like this week, yes. Yes, and then next week will be my last week, and then I will stop the classes temporarily for Ramadan. Then inshallah, after Eid, we will resume. Okay. Sixth graders are welcome. They are more than welcome to join us, you know, with the fifth graders, because we will be starting. We are not, you know, like studying the basic ideas. So yeah, it's good. It's good for your revision. You know, I have seen many of the even seventh graders, they don't know what ions are, what cations are, what anions are. They don't know how to write formulae. They don't know the symbols. So yeah, that's a problem. So it's good that you guys attend and you'll revise. Okay, any other question? So should I end the class? Okay. Okay, Jazakallahu khairan.
Allah Hafiz, ma'am.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz. Allah Hafiz. Allah Hafiz.
Hafiz, ma'am.
Allah Hafiz.